Alrighty, folks, so we finished sedimentary rocks, at least this semester, fall of 23. And before we go on to weathering and erosion, we're going to take a quick sidestep into the world of metamorphism. I don't talk about metamorphic rocks a whole heck of a lot. I don't want to say that I don't like them, but they don't do a whole lot for me. There's a handful of pretty cool looking ones. We would be a pretty poor civilization if it weren't for marble. We made some amazing statues out of marble. And gneiss is pretty cool looking. Gneiss is nice.
I was going to say that.
But other than that, oh, and slate. We love slate. All right? Really like slate. From pool tables to sidewalks to roofs. Well, that's about it. Every so often people will paint a picture on slate and hang it on a wall. Other than that, I think I'm finally out of other than that. Metamorphic rocks, we can't even see them being made. It happens deep, deep down in the earth. We know they are made. We know they're changed rocks, metamorphosis, right? That's where the word comes from. So, we talk about them a little bit. And then we see them in lab and we talk a wee little bit more of them. And then we're done. So we're just going to take a little pit stop, as I said, and talk about metamorphic rocks in the process of metamorphism. That's a very nice picture of gneiss there again, and that's gneiss with a G. It's the bandy, swirly rock. Huh. That's weird. Wonder why that slide shrank. Sorry, I really feel the need to fix that. There we go. Now it's not Metamorphos M anymore. So metamorphism. Definition of metamorphism. Mineralogical and or textural changes that occur in a rock due to exposure to extreme pressures and or temperatures. Mineralogical changes, textural changes due to exposure to really high temperatures or temperatures and pressure. I always get caught up in the and ors. If you don't word it right, it's absolutely wrong. I believe that's the right way. We want it to be, because you're going to get temperature no matter what. But you don't always get the pressure is the thing. Okay? You don't always get the pressure. And as I implied, this happens deep, deep down in the earth. For the most part. So, factors that cause metamorphism, we've got two. Changes in temperature and changes in pressure. We'll tell you how you achieve both of those, of course. Oops. All right, so the easiest way is to bring the rock into the earth. Well, how the heck do you do that? Plate tectonics? Probably the easiest, and that's by no means easy. Your book is going to talk about burial. I mean, by argumentatively, you can support the idea that, you know, the more stuff you pile on top of you, the further down you'll be. But also, that sort of also just builds up what's on top, right? That doesn't necessarily mean you're getting closer to the core. So that's a tough argument, especially if you don't quite get what they're talking about. So picture just literally plate tectonics, conveyor belt, bringing it into the earth. Don't worry about how weird it would be for that to actually happen, but it does happen. Okay. So remember the geothermal gradient, we talked about that. There's a slow gradual increase in temperature as you go into the earth. So that's how you get there. And by the time you get to the core, you're at about 9,000 degrees Fahrenheit. Now these guys aren't going anywhere near the core, okay? But it's hot in there is the point. Another way, all right, other than bringing the rock to the hot, is bringing the hot to the rock. We actually talked about this briefly when we did igneous intrusions. Remember dikes and sills and plutons? And on the test, there was that one weird word that I didn't talk about called bake zone. All right? Bake zone is that area around the intrusion that is affected by those high temperatures of that intrusion. Kind of like putting your marshmallow into the bonfire, or your feet or your whole body close to the bonfire to get warm. The marshmallow actually changes, though. Hopefully you don't melt your shoes or anything. So, so that is an example of hot spots, igneous intrusions. A couple examples of the hot coming up closer in the mantle. There was a question the other day about Yellowstone. This happens just coincidentally to be a little picture about what's going on there. So, while we don't really want to talk about burial helping you with the heat, it certainly does help with pressure. So, if you got a whole bunch of stuff piled on top of you, again, talk about seasons. Football's going on right now. Well, you may not have ever played it, professionally. You may have played it in the backyard. And the more people that pile on top of you, the more weight or pressure you've got pushing down on you, right? You've never done that. Perhaps you've played a game of Twister. Same idea is true when everybody collapses into that tangled pile. We call that lithostatic. Lith is another word, we mentioned it before, but another word for rock, okay? Static, stasis, constant. So it's constant rock pressure. And it's more or less just a squeezing. It's one directional. I don't get into that on this slide, but the next one talks about how it's not equal or not even. So we might as well mention that lithostatic pressure is fairly even. It's just a squeezing, pressing down, flattening out. Tectonics, on the other hand, think about two plates moving around and one of them eventually crashes into another one. They call that differential stress. The force is coming from not all directions evenly, okay? This is the kind of stuff that builds mountains. Very, very slow car wreck. We talked about India trying to join Asia, and in between is that crumpled up mess that we call the Himalayas. All kinds of metamorphic rocks up in there. You guys live in the northern portion of the Appalachians, which they call the Adirondacks. There's metamorphic rocks all through there as well. You got a whole bunch of sedimentary on top of them, so you hardly ever see the metamorphic stuff, but it's up there. You got to look way deep down in, but it's there. So through burial, you could find metamorphic rocks just about anywhere. But tectonics, it's got to be somewhere where there was some interaction at some point. This is just an example of lithostatic, okay? You've got more or less the same pressure all around. You don't think about it, but the ground is pushing up against you as you're pushing down. That's where the equal part comes in. I'm not sure I could agree with the last diagram there with the shoe on it, that the left and the right pressures are equal. I suppose if we're talking about air pressure, sure. But at any rate, at least the up and the down arrows we can agree with rather easily. Because you're not moving the ground, right? So the ground must be pushing up against you with equal, if not greater, force. Differential, and this is supposed to be a deck of cards, I think. And you're pushing in one direction. There's very little resistance, so those cards sort of slide off to the side. Done that, if not accidentally, at any rate. Not a huge deal, just want to make sure you guys understand the difference. All right, delta T and delta P. If you haven't had a science class recently or never or completely forgot, the delta is a great little easy shortcut way to say change. All right? And you can, as you see here, you could even type it. You have to get that special keys combo, but it works. So mineralogical changes come from a change in temperature. Textural changes come from a change in pressure. And remember, foreshadowing a little bit ago, we have some rocks that are affected only by changes in temperature, and we have some rocks that are affected by changes in temperature and pressure. You can't get just pressure without temperature. Yeah?
Why wouldn't they put delta T on textural and make mineralogical like delta M or something?
Well, because it stands for a change in temperature and a change in pressure. The T is for temperature and pressure. Yeah. It's just unfortunate that the T matches up sort of there with textural. But yeah, so T, textural, change in text. I see where you're going with that. No, stands for temperature and pressure. It goes back to chemistry and or physics. Little t, lowercase t is time, capital T is temperature, and capital P is pressure. So. Everyone always takes their sciencey classes because they think they're like easy. It's actually all the sciences wrapped into one, but we do it so cleverly you hardly ever notice. We are all the sciences. Okay, so what are mineralogical changes? Mineralogical changes, there's a couple things that can happen. The first one is what we really see the most of. You throw it sort of back in the oven, is the way I talk about it in lab. All right, and then again, this gets a part 2 lecture when we go to lab. The big one that we see that's super easy to process is quartzite. Quartzite was a hunk of sandstone in its previous life. So you take sandstone, you've got this gritty little rock made up of grains of sand glued together. You throw it back into the rock oven, and it turns into this big crystal, solid, durable, actual hunk of rock. Okay? What happens is that those little quartz grains that are in the sandstone grow bigger, and as they're growing bigger, they meld with a D, meld together, grow together, all right, and it becomes this interlocking mass of quartz. Also, you can see recombinations happening. You get that sucker hot enough, it literally kind of turns into a water balloon sort of thing. It still has its skin on it. It's still a rock, but the inside is such a molten, mucky mess that some recomposition can occur. Okay, but primarily we look at the first one, or we get to see the first one. Slate is another one. I'll save that story for lab class, but slate's another great example of that. And it's just an example.
So it's like the grains melt and spread out a bit?
They melt and grow together. Yeah. All right. Vocabulary word. Foliation. When we talk about textural changes, they're going to use the word foliated. Foliation is an orientation of grains into a direction. That direction is usually that of the stress. Remember pushing on those cards? Which way are the cards going to go? Well, the way you're pushing, of course. Okay? So if we've got two continents crashing into one another, and one of them's pushing harder than the other, let's say, again, India smashing into Asia, Asia's not really going anywhere, but India's the one that's moving. So let's say India's moving due north. The stress, all the crumpling, is kind of going to be aimed northward because that's the stressor there. What you guys end up seeing this as is some sort of organization in the rock. All right? And again, this relies heavily on lab. We're just sort of foreshadowing lab. It's not going to be random. Think about granite, how it was just a smattering of minerals all over the place. Well, you heat up that granite, you apply some pressure, and that stuff actually starts to sort of line up and organize a little bit, get their ducks in a row, if you would. So it's usually quite obvious when something is foliated. Not always, but usually. And the cool thing about it, again, the direction of, if this stuff is still in place, not sitting on a table in a lab somewhere, but if you're literally still out in the wild, you could reconstruct more or less what happened. You can see the direction of foliation and say, oh, the stressor came from the northeast, and so on and so forth. And again, there's very few people on the planet that care what happened 10 million years ago, but there are a handful, and when they can find out neat little tidbits like that, they like to. So it does matter to somebody somewhere. Our opening slide was a great example of foliation. This was, for all intents and purposes, probably a diorite. Remember, diorite was just black and white, black and white, black and white all over the place. But you heat it up, you squeeze it, and it starts to line up with minerals. Minerals will go next to the other minerals that are like it, and so on and so forth. I can't explain that bit much more than that. It still blows my mind that it forms stripes. I had an entire semester on Metamorphic Rocks a long time ago. But our teacher that semester was this cat he had just graduated from UC Davis, which is a University of California, fairly prestigious geology school. What the hell he was doing in Youngstown, Ohio, I have no idea. But he was there, and he talked about 1.5 feet over our heads for 14 weeks. I think we had quarters, so it was probably 12 weeks. We don't understand a thing. And we were like seniors. All right? We just kind of sat there and smiled and nodded and occasionally blinked at him like you guys are doing to me. But again, we had 3 years of geology. We still don't know what the hell he was talking about. So, anywho, so it's still a mystery to me. And maybe that's where my disdain for Metamorphic Rock comes from. Is Dr. Ray, I don't know. But he was a good guy, as it turns out, but just he didn't know how to talk to undergrads very well. But it lines up, okay? And you'll see this. You're going to, again, this is a hunk of gneiss. You'll see this. I could understand the swirling. Okay, I get it, that the rock that hits a bend, it's fine. But the fact that, and again, this is where the temperature part comes in. The fact that it must have got so hot in there that all of the quartz and the albite, they just sort of reconstituted and grew a new band of crystals. And then apparently the pyroxene or the augite, whatever you want to call it, did the same thing and so on and so forth. I just don't understand why it stripes. If you see a striped rock, though, call it nice, and you'll be good. At 101 level, that's what matters. Oh, that's a hunk of gneiss. Add to the fun that this is gradational. This is a spectrum. This is a baked potato in the microwave, as I usually say. Imagine if you could, and nowadays with our cameras you can, It's sort of a time lapse. There's no reason you would do this, but you could. Put a time lapse camera in front of your microwave, throw a baked potato in there, and set it for like 12 hours. Okay? And you're going to see all the changes that baked potato goes through. From being not quite done to perfectly done to overdone to on fire to wherever's next.
A hunk of something black.
Charred carbon, yeah. Same thing happens with metamorphism. The longer you're exposed to the temperatures or the pressures, the more changes happen. Okay? We talk about low grade versus high grade. Low grade metamorphism is a little bit. High grade metamorphism is a lot of it. And your words that you're going to see, your metamorphic names, there's slate, there's schist, there's gneiss. Well, we also use those as adjectives. Slaty, schisty, gneisic. I don't know why they don't say gneissy, but they do say schisty, and everybody usually giggles. So we talk about those as textures because they're very common enough. So you could actually get these sort of blends, okay, where you have a really schisty slate or a really nice schist, and so on and so forth. There's another joke you missed. So anyhow, that's gradation. You're going to see it in lab, and that accounts again for some variation that makes identifying these annoying for you guys, because not all schists are as shiny as others, but shiny schist is a good thing to remember, because most schists are shiny. Go ahead.
When I saw schisty, I read that shisty, and that was pretty funny in my head.
Ah, well, either way. I imagine there's some folks across the pond that do call it shist. But whatever works for you, however you remember it, it's kind of like a limonite kind of thing. But usually we say schist. All right, and then we've got this straight line metamorphism, which again is something I'm going to teach you in lab. Well, here there's a slide for it, but still we're going to teach you in lab. So within that gradation, we do have stopping points that we recognize. All right, you take a piece of mudstone, you throw it in that metamorphic oven, you leave it there for a little while, it turns into something we call slate. You leave it in the oven longer, that slate turns into a schist as the crystals start to get bigger and bigger, and then all the way through till gneiss. And if you leave it too long, who remembers the rock cycle diagram? We just got done more or less talking about the rock cycle. What's the step beyond metamorphism? Yeah, remelting. All right. Right before we've got magma or lava, we've got that arrow that was the step of remelting. You leave it in there too long, you can't burn a rock, but you can melt it. Okay? And that is beyond gneiss. So, again, this... Huh?
It would be awesome beyond gneiss.
I suppose. So this is when you have heat and pressure. Okay? These are foliated metamorphic rocks. It's going to be roughly half of your metamorphic rocks that you see. And then we have a handful that are non-foliated. They're not bothered by pressure. They're just temperature. And those are very simple. This changes into that. That changes into the other thing. We already mentioned a couple. Sandstone to quartzite. Limestone to marble. Mudstone to slate. Those are non-foliateds. One more vocab. Protolith.
Beginning of a...
Yes. Proto means earlier first. Prototype. Protozoa. Protozoa means first life, right? Early life. So, this is first rock. What I call parent rock. And what some of my teachers call it too. But the real word is protolith. What it was before it became metamorphosed. Yeah, I don't know if that's a word, but we use it in here. We just gave you 3 examples. Sandstone would be the protolith for quartzite. Limestone would be the protolith for marble. so on and so forth. And again, if you're exploring the past of the area, doing some paleo-environmental work, okay, and you want to know what's going on there, it's very helpful to know what the original rocks were, because then you also know that there was some sort of tectonic event or igneous intrusion event or something that happened here after that fact. All these clues start to pile up on one another. It really is like an investigation. It's kind of cool. Going back to the foliated just for a moment, you still want to know the parent rock. All right? So the parent rock is just the step before it. So the parent rock for schist is slate. Parent rock for gneiss is schist. Parent rock for slate. They have the word low grade there. Whatever. The parent rock for slate is a mudstone. Usually in lab I say shale. This morning for some reason I've been saying mudstone. But remember, shale is a mudstone. Those of you that had lab already know that. Those of you who have lab tomorrow will know that tomorrow. And those of you at home will know that when you do sedimentary rocks. So this is a good list to know. Again, in lecture, I'm never going to show you a hunk of something. But I guarantee you, if I come up with 48 questions and I need 2 more points to make that nice, easy 50-point test math that I like to do, I'm going to whip some of these guys out, okay? Just like sandstone is plastic, chemical, or organic, fill in the blank. It's fair game. We already tested on igneous rocks this semester, so that wouldn't get thrown in, but you certainly saw enough questions about felsic intermediate and mafic on there. So the only one we don't know is the bottom one. Those of you that had lab yesterday, what's a good guess?
Peat.
Close. Close. Similar, but not quite. What was the coal you guys saw yesterday? Yes, thank you. B coal, bituminous coal. All right. Bituminous coal undergoes exposure to high temperatures. All those nasties get baked out of it, and it turns slightly better for us to burn. Something called anthracite coal. Back in the day, that was called rich man's coal because it was a cleaner burn. Definitely more bang for your buck, I think, as far as BTUs and all that go as well. I'd like to think these days in the world that we live in that all we burned is anthracite coal. I'm sure that's not the case because there's way more bituminous coal than there is anthracite. So I at least hope that we burn some sort of hybrid of a mixture of the both. I still can't picture in 2023 a dump truck full of coal pulling up to a power plant and dumping it into the burner. I'm sure there's some intermediate processing where we've got like wood pellets, pellet stoves and stuff like that where we make these coal pellets or something. I don't know. But I do hope we are hybriding some anthracite into our coal as we burn it. It is a bit cleaner. There's no such thing as clean coal. But anthracite's as close as you're going to get.
Maybe in the future we'll make some sort of machine that's able to create enough heat and pressure to make anthracite coal.
That would be awesome. Process the bituminous into... yeah, it's like Superman squeezing the coal into a diamond almost. But this is slightly more achievable. That's a neat idea. You get out of here, go get an engineering degree, and make that, okay?
We should nuke rocks, yeah.
Nuke them. I didn't suggest that. That would introduce a whole other level of problems. Nuking rocks, yes. All right.
What would that do to a rock? Would it change it, or is that still not enough?
So we, yeah, kind of. with asteroid or meteorite impacts, we see something called shock quartz. We also see it with nuclear blasts, areas where we've blown stuff up. But meteorites and so on and so forth, they can create enough force and pressure and heat that it puts these little microfractures through the quartz. It changes the quartz. We've talked about lightning. We might not have in this semester, but we talked in the past. Lightning, when it hits sand, melts it instantly to glass, and it leaves these cool little trails, if you would, tubes called fulgurites. And so you could actually see some change there. But full-on metamorphosis, I don't know. But I do like this idea of processing bituminous coal into... That may even be going on, not necessarily into making it anthracite, but attempting to clean it up in some way, shape, or form. So what we've been talking about, I didn't use the word, but what we've been talking about is sort of large-scale, or what they call regional metamorphism. Where, a continent smashing into another continent. That's a big deal, okay? This is a little bit more on the spot. This is what we call the contact metamorphism, and I've mentioned it to you a few times already when we talked about those igneous intrusions. This is that bake zone stuff. This is the marshmallow coming into the bonfire, okay? This is only an exposure to high temperatures, so it makes the non-foliateds. And while you may not see the matching of parent rocks that I dangled on in front of you a couple minutes ago, you definitely will see an application level question like this, okay, where I'm actually asking you to put a couple things together. So let's just practice one now. I've told you a couple times this one, so it should be an easy guess. If some magma intrudes into a layer of limestone, all right, and causes contact metamorphism on that limestone, what kind of rock are you going to find surrounding that igneous intrusion? What's the name of the rock, I should say? If you bake limestone, you get... Anybody?
Is it a rock we saw in lab yesterday?
Well, no, because we're making metamorphic rocks.
I don't know, metamorphic rocks.
Yes, what do we call that? I've told you guys 6 times this morning. You're drawing pictures, so that's easy to, here for you not to remember it. But these other guys are actually taking notes. Go get some water. Or you got something right there.
I'm good, I just spit coffee.
Okay, what do you get when you metamorphose limestone, folks? All right, well, you'll learn next week. I could hear the people at home shouting their answers out now. What do you get if you metamorphose sandstone?
Quartzite.
Beautiful.
Oh, wait, limestone is marble.
Yeah. Yes, thank you. I knew you were listening. So if that magma intrudes into some pre-existing rock, it has to, or it couldn't intrude, right? It's going to change it. That bake zone, that area around it is going to get altered. If it intrudes into limestone, it's going to make a layer of marble. If it intrudes into sandstone, it's going to make a layer of quartzite. If it intrudes into a mudstone or shale, it might likely turn it into a slate. Okay? Learn those examples. I know we haven't had it in lab yet, but I have seriously said it several times today. Now that I'm saying it, it sounds familiar, right? So these bake zones literally happen right around. I use the bonfire example very purposefully. Okay, because as you approach the bonfire, you don't necessarily feel it till you get right up close. Or more so, as you back away from it, you feel it less and less and less. So these bake zones are literally these buffers around the intrusion. So if you were to see this as a road cut, driving down the road, you're on the thruway, and you're coming through all those beautiful rock cuts over there, and for whatever reason there's a giant igneous intrusion in the middle of it, you should see just to the left or the right of it, or the top or the bottom, depends if it's a dike or a sill, right? you should see some change in the rocks. All right, that's contact metamorphism, and it makes a new rock. All right, so wasn't kidding. Handful of slides. We don't do metamorphics a whole lot. You will get a good bit more of that in lab. All right, when we get to metamorphic rocks.